In the last class we were, or the last few classes, we studied how to understand the vector fields around equilibrium points, but there we started with the first order definition of the differential equations. That means, we started with x dot is equal to some function of x and y dot is equal to another function of x and y. But earlier we have seen that this is initially obtained in form of the second order equations by the Lagrangian method, and then we reduce it to first order. So, the natural question is, if we first obtain it in second order form, then why not try to analyze it in the second order itself, and we can do that on the basis of what we have already obtained in first order. So, that is what we will try to start with today. So, normally the equation will be given in the form, if q is a state variable, second order equation would be d2 q dt2 plus something times dq dt plus something q is equal to 0. Fine. We normally have equations given in this form. Why? Because suppose you have a simple pendulum, initially when you obtain the equation it would be in this form, and then we understood how to obtain in the first order form. Now, in many cases it would be simpler to obtain in this form. For example, if you have a circuit, say there is an inductor, there is a capacitor, and there is a resistor. How will you do it? Well, there are hundreds of ways of doing it. It is very trivial, very simple, but ultimately you will apply the Kirchhoff's laws, and when you apply the Kirchhoff's laws, you will find that you either obtain it in form of the capacitor voltage or in form of the inductor current. If you obtain it in form of the capacitor voltage, it comes in this form. So, suppose the charge here is q, then at this point you have the current flowing is c dv dt or q dot. At this point it is the voltage divided by the resistance, and at this point it is the I, which is also state variable. So, you can easily write it in this form. I am not going into this because it is trivial. The point is, often you will find that it is easier to obtain it in this form. So, on the basis of what I have already understood in first order form, can we understand it, understand the dynamics, understand the behavior if it is given in this form? Now, in considering that question, it has become customary to express this term as twice zeta omega n and this term as omega n square. Why? I will come to. So, that the equation becomes d2, I will write in the other page, d2 q dt2 plus twice zeta omega n dq dt plus omega n square q is equal to 0. So, normally these are numbers, okay, but whatever the numbers are, we express it in this form. There is a reason for it. I will illustrate a little later. But firstly, how do you proceed to solve this kind of a differential equation? You have learned in mathematics, right? What we do is a trick. The trick is to write the ddt as p and then write an equation for that, right? You have learned that. So, it will be p square plus twice zeta omega n, it is p plus it is omega n p square q, which one? Yeah, this is p square of q. I am writing it this way. Fine. What? Square. Yes. Now, this you have probably learned in mathematics class, that you can solve it this way. That means d dt simply written as something p and write an algebraic equation like this. Do you know why it works? It, to me it looks like a mathematical sleight of hand, right? So, why does it work? After all, dt is not something like a number or p, but still it works. Why?
So because the solutions of this are going to be of the form exponent.
Yeah, why? The reason is that after all you are trying to solve an equation like this. Notice that it is a combination of q, the derivative of q and the double derivative of q. So, something, what that something is we do not know yet, something whose derivative plus the double derivative with some coefficients should yield 0, and therefore, this and that must have the same form, otherwise this cannot happen, right. And what is the function that you know which has this property, that its derivative and double derivative have the same form? It is the exponential. So, in general the solution would be some number times e to the power, say some kind of exponential, right. If you use this as the possible solution, then how can you write this? It's, if this is the solution, then dq dt is k p e to the power p t, and d2q dt2 is k p square e to the power p t, right. So, if you substitute it here, then you have k p square e to the power p t plus twice zeta omega n k p e to the power p t plus omega n square k e to the power p t is equal to 0. You would immediately notice that this yields this equation. Check that. So, this cancels off, k cancels off. So, ultimately you get exactly this equation. So, what you ultimately yield from this equation is p square plus twice zeta omega n p plus omega n square is equal to 0. So, this is the characteristic equation. So, today we are talking about second order differential equations, and we had started with something like this, d2q dt2 plus something dq dt plus something q is equal to 0. These somethings are numbers. Then we said that we will normally express it in this form, so that the second coefficient becomes twice zeta omega n, and the third one becomes omega n square. Why we will come to. And then we said that this yields the characteristic equation this. Now, what are the roots of this characteristic equation? Obtain them, obtain the roots. Quadratic, so it is easy to obtain. P1 and P2 are minus zeta omega n plus minus root over it is 4 zeta omega n, 4 zeta omega n square minus 4 omega n square. Sorry, it is 2, it will ultimately be 4, yes. So, this becomes minus zeta omega n plus minus, I will now cancel the 2, you have omega n comes to the front, omega n root over, it is zeta square minus 1. Now, this is why we had initially expressed it in this form. Why? Because it says okay, we'll come to that little later. First, let us try to obtain the solution of these equations in terms of what we already know. What we already know, we know how to obtain the solutions for first order differential equations. So, we will make the similarity. So, from this let us obtain the equivalent first order definition, because that is what we already know. How do you obtain this? That can be obtained by assuming q is equal to x and q dot is equal to y. So, if you proceed, you get x dot is equal to y and y dot is equal to that whole thing. Y dot becomes this thing taken to this side. Yeah. It is minus twice zeta omega n y minus omega n square x, which means it is x dot y dot is equal to, expressed in the matrix form, 0 y is 1 minus this is omega n square and minus twice zeta omega n x and y. Fine. So, this is the equivalent first order equation form whose solution we know. How do you solve? You obtain the eigenvalues of this. Obtain the eigenvalues of this matrix. The eigenvalues of this matrix will be given by, this is minus lambda 1 minus omega n square, this is minus twice zeta omega n minus lambda, this equal to 0. Fine. This yields, if I keep it displayed here, this yields lambda times twice zeta omega n plus lambda plus omega n square is equal to 0. Lambda square plus twice zeta omega n lambda plus omega n square is equal to 0. Notice that this is the same, exactly the same as the characteristic equation that you had obtained. So, which means that if you have a 2-dimensional form, then its characteristic equation is the same as the equation that yields the eigenvalues for the first order form. So, the roots will be the same as the eigenvalues. The roots will be exactly the same as the eigenvalues. So, in this case, what are the eigenvalues? We have already obtained. Yeah. So, lambda 1, lambda 2 are minus zeta omega n plus minus omega n root over zeta square minus 1. These are the two eigenvalues, and we know that such a system, such a set of two first order differential equations, their solution will be given by the character of these eigenvalues. If they are real and distinct, then there will be one kind of solution. Real and equal, there will be another kind of solution, and the complex conjugate, there will be another kind of solution. So, under which these three possibilities will pertain, tell me. See, firstly, when will it be real? When zeta is greater than 1, clear. So, eigenvalues if zeta greater than 1, clear. Zeta less than -1, zeta less than -1, right. We'll consider that issue a little later. What is zeta? We'll understand, and then we'll talk about that possibility, because zeta actually comes from the frictional terms, so that normally doesn't get negative. So, this value represents the condition for the real eigenvalues. If it is exactly equal to 1, then this term is 0. Then this term is 0. You have what? Yes. Fine. Firstly, when you have the value as real and greater than 1, then what is the solution? Let us see. The solution then will be, which you already know, q of t is equal to, this is the real part, and then this is the, no, the whole thing is real part. So, it is one plus another minus. So, accordingly you write what is the solution of this. There are two eigenvalues which are both real. So, you have e to the power. So, when it is real, take omega in common, and what remains? Minus zeta omega n t C1 e to the power omega n root over zeta square minus 1 t plus C2 e to the power, is it visible? Yeah, minus omega n root over zeta square minus 1 t. Visible? Yes. Fine. So, there are one plus another minus. This part is here times this part which is here, clear. So, that will be the ultimate solution. It is clear that depending on the value of this term zeta omega n, you have the exponential decay. So, that is the condition of either it being real or complex, and that is exactly why we wanted to express it in this particular form, this specific form, so that the zeta becomes clear. What is the role of the omega n? Omega n's role will be clear when you consider the complex conjugate eigenvalues. So, when you have complex conjugate eigenvalues, that means eigenvalues. Okay, let us consider second the real and equal, then we will consider the complex conjugate. When does that happen? Zeta is equal to 1, that is the critical case. Then the solution will be, you have already learned that, let us see, q t is equal to, what will it be? What will it be? Yes, it is, no, there are two components. One component is e to the power minus zeta is 1 omega n t times what? Yes, C1 plus C2 t. So, that will be the solution in that case. Now, let us come to the third case, where the eigenvalues are complex conjugate. When does that happen? That happens when is less than 1, fine, or you can say like this. Then what are the eigenvalues and what will be the solution? You have already learned. So, write in that form. It is, in that case we have to write it in sigma plus j omega. So, eigenvalues complex would be sigma plus minus j omega, where sigma is minus zeta omega n and omega is omega n root over zeta square minus 1. Sorry, 1 minus zeta square, because you have to get a negative out of it, fine. So, these two are the zeta and the sigma and omega. So, in that term now we can write it yourself. In that case the solution is q t. I am not illustrating the whole thing. Why? Because we have already done it, and the solution is exponential, the real part first, it is minus zeta omega n t c 1 e to the power j omega n root over 1 minus zeta square t plus c 2 e to the power minus j omega n root over 1 minus, I am now doing the other possible way which I stated. These are two eigenvalues, we simply write in terms of that, and then if we simplify that, it will always yield something like, yes, we can write it as a then e to the power sigma t times or sin omega t plus, we have already seen that. So, I am not illustrating, the point is we start and then we arrive at this point. So, here you have some amplitude, some sinusoid and some exponential envelope on which it is done, and the exponent is in this case minus zeta omega n, clear. Now, let us see. In this case, your omega, the frequency of oscillation of the sinusoid, is not really the undamped natural frequency. It is somewhat modulated by this term. It is slightly different. This is the reduction term. This is the exponential term here. So, these two will ultimately govern the behavior, but in order to understand, so what will be the behavior like? If the sigma is negative, then it will be fine. So, if the zeta is between 0 and 1, the behavior is normally like this, but depends on the value of sigma, and the sigma is zeta omega n. So, that tells us whether it will be exponentially growing or reducing. Fine. Now, notice that when we chose these particular terms, they have the relation that if you write sigma square plus omega square, can you write that? What was sigma square? It was zeta square omega n square plus omega n square into 1 minus zeta square, fine. This comes to So, this is another reason why we do it this way. The point is that in that case this and that square is this, which means it is the Pythagoras, right, Pythagoras equation. So, you have, if this is the complex plane and if you are trying to plot this, this is the real part will be plotted along this is the imaginary part will be plotted along that, and then if zeta satisfies this condition, then the eigenvalues would be complex conjugate, say like this, sorry, this part will be omega and this part will be sigma. Now, suppose I change this, as a result of which this moves, what will happen? Yeah, this tells us that this will always traverse on a circle. There will be two complex conjugate roots or eigenvalues, complex conjugate, and these complex conjugate eigenvalues will move like this. Fine. So, if you are changing zeta, keeping the omega n constant, then it will move on a circle with a radius of, what is omega n? Omega n is, you can see, if you look at this, if you put zeta 0, then what has happened? This comes to 0. As a result, you get a purely sinusoidal oscillation with frequency of how much? Omega n. So, if the system has no zeta, which means this term is 0, this term is actually resulting from the friction in the system or the resistance in a circuit. If you go back in your thought to the way we were deriving the equation, this term comes from there. So, in that case, the natural undamped frequency is omega n. Natural frequency of oscillation, say a LC circuit, which you leave to itself without any friction or something like that, without any resistance, then it will oscillate with a certain frequency, and that is that. So, if you now add a resistance, then, and if you keep varying the resistance, then it will keep moving like this, and then after some time, say you change the resistance, it was moving like this, and after some time it will collide. At this point, this equation will be, where is it? Where did I keep it? Okay, that equation we just wrote, which pertains for real and equal eigenvalues, that will be valid. And after that, what will happen? One will move like this, the other will move like that. So, they will go out, and then the first equation that we wrote, that will be valid. Clear? Because of these conceptual advantages, we always express second order equation in this form. Let us do some exercise. For example, if you have an equation like q double dot plus 5q plus 4 is equal to 0, what will be the behavior? Can you immediately tell? What will I do? We will simply say this is the omega n square. So, omega n is equal to 2. This thing is twice zeta omega n, 2, and this is 2, this zeta is 5 by 4. So, this gives zeta is equal to 5 by 4. What will be the behavior? What will be the behavior then? It is greater than 1. So, it is real and distinct, and therefore, the behavior is going to be exponentially decaying. So, without solving the equation, we could directly tell. Fine. So, that is exactly why we do this. We always try to express in this form. Suppose this is the equation that we have is something like that, q double dot plus say 5q plus 9. What will be behavior? Decaying sinusoid. How do you know? Okay, in this case your omega n is 3 and zeta is 5 by 6. So, this is less than 1 and therefore, it will be decaying sinusoid. When will it be a growing sinusoid? Which term is negative? So, this term is negative, yes, it will be growing sinusoid. Fine. So, can this term be negative? No, it is omega n square. So, that is how we figure out how the behavior will be just by looking at the equation. You do not need to solve really, and unless you do this exercise, you will always be constrained to solve equation, then only say this will be the behavior. Fine. So, at this stage let us do some simulation with the computer. Let us take a second order system and we will do it by bond graph. What is a good second order system? Can you show the computer please? Yes. So, what is a good second order system? A mechanical system in which you have a mass, spring, damper with some forcing. Mass will give one state variable, spring will give another state variable, nice. And you have already seen that is nothing but electrical equivalent of a series circuit. Let us do that, because it is second order we can test. So, first it will be one junction, then it will be an AC, then it would be an I, then it would be a C, can you see that, then an R, then we will connect by the bonds. The lines are somewhat thin, is it visible there? Good. Okay. So, after we have connected, we will give the numbers, we will give the power directions, we will give the causalities. If you cannot see the causalities because the circles are there, we will drop the circles, hide circles, yes. So, you can see are the causalities right? AC is receiving the flow information, I is giving the flow information. So, in one junction the flow information has come, it is distributing in the other bonds, is fine. In any case that needs to be tested. So, check integrity, it says 0 errors, 0 warnings. So, we are fine. Then it is to generate equations, I have pressed it and it has already written the equations. Probably they are too small for you to read, is it? Okay, I will read it out. E2, which is the second bond here, is AC1 like that minus R3 times P2 by M2 minus K4 times Q4. The state variables are Q here and F4 is P2 by M2. F4 is P2 by M2. So, these are the two equations, that is what is expected, fine. Now, we have already generated the equations, now we have to define the maps. What are the state variables? Q4 and P2, we could give a name, but we understand what they are. So, let us leave that. Then it is to generate the simulation code. I will give it as bond graph 2 same, it overrides, fine. Now, we have to compile, this is a compilation. So, set and compile, let us see what it writes. Okay. So, it says 0 errors, 0 warnings, so we are happy. then we go to the simulation, make it bigger, good. In the left hand side it shows the 4 parameters in the system and we can set their values. Say we set AC1 as 1, M2 what, say 1 kilogram, K4 say 10 and R3 may be a small value. Now, write down these values, write down these values. M2, M the mass is 1 kg, K4 is 10, R3 is 0.5. Okay. In this case, the bond graph was let us come back here, yes, 1 SE I R C, fine. Now, in this case your circuit is simply fine. For this you can write down the equation yourself, no problem, and it will be a second order equation. Write it down and tell us for these parameter values what do you expect the behavior to be. You understand what is the exercise? Exercise is for this, write down the equation in the second order form and from the parameters that you have, what do you expect the behavior to be. The circuit is too simple. Do it, do it, do it. Quickly write down the equation, substitute the parameter values and tell us how will it behave. Come on, do it fast. This is a simple question. I did not give a tough problem. This is a very simple problem. What will the behavior be? Yes, Vamsi, why are you taking so long? Huh? Decaying sinusoid? Okay, let me, tell me the equation. Q double dot plus 0.5 Q dot 10 is equal to 0. Can you in general give these values, that means in terms of the parameters? So, Q double dot plus L Q dot plus I 1 by L C is equal to 0. Q by L C, yes, fine, okay, good. For these things you have already found it that it will be a decaying sinusoid. Let us check. We will start the simulation at 0 time and we will end it at 10 seconds, and then I have to set the plot blocks, yes. So, horizontal is time and the vertical 1 is P2 and the vertical 2 is Q4. Fine. Now I will simulate. Okay. So, it is a decaying sinusoid, can you see that, and the two are out of phase with each other by some value. What value do you expect to be? Okay, check that. So, this, and in the phase space, in the state space, it will be incoming spiral. Let us check that. So, horizontal will be then P2. Okay. This one I do not need, so I will none. Sorry, this one will be Q4. So, the behavior is a decaying spiral, starts from here and goes on. Where does it ultimately converge? Equilibrium, where? At what value does it ultimately converge? Yes, there is a input voltage, and therefore, it will not converge at 0 0. It will converge somewhere, and it is actually converging there. It is not converging at 0 0. Fine. Now, tell me, how should I change these parameters so that I will get exactly a equal roots, equal real roots? How should I change? When will you get the roots exactly equal? And what should I do in order to make it real eigenvalues? R equal to 2 will give? No, for that quickly write down the characteristic equation and the eigenvalues for this. Quickly write down the eigenvalues for this. It will be minus R by L plus minus R by twice L root over is that right? By 2. So, when will it be exactly equal? We have to just set this equal. So, what value of the parameter? Say R equal to something, given LC constant, root over 40, bad number. It is difficult to set that. Okay, so equal roots would be, give me good suggestion. L is equal to 1, R is equal to 1, C is equal to 4. Okay, fine. And for what condition will it become real and distinct? R less than, R greater than this. Good. Let's check. Let's check. So, we will set the parameters again. M2 was 1, which is L is 1. K4 would be 0.25, yes. And R would be 1. Fine. Then it should be okay. Let us at this stage plot it for the horizontal axis should be time, and no, not this. I have not replotted simulated. Vertical axis should be Q4, and yeah, this looks okay. Now we have to resimulate. Aha. Okay. So, this is the kind of response you expect from a critically damped system. It is reaching that, not yet. You want to simulate further? Let us see for a longer time, 20 seconds. Fine. It is reaching that value, but never going above or something like that. Fine. If you see that in the state space, then I will have to plot this as your P2 and this as your Q4. Fine, difficult to see, because in this case you are not seeing the equilibrium point, but it is going to the equilibrium point that way. And you said that if you raise R beyond that, then it will be two distinct ones. Fine, let us set that. So, let us set it 2. Happy? Let us check. Now, I want to set these things proper. I want it to be time, and I want this to be okay. Now, let me simulate that once again. See, if you want to simulate it for a longer time, let me say 100 seconds, I do not mind that. So, from there it is going, or we can set the timings to 0 to 100. See, it is going and then it is decaying. 100 would be a bad time. So, let me change it to 0 to 50, a nice thing to see. Okay. So, it goes and then it. Now, what did I plot this time? I plotted time and P2. P2 is the current through the inductor. Notice the circuit, the current through the inductor, because of the capacitor, must go to 0. So, it goes up and goes to 0, but what is the capacitor voltage? That will stabilize to some other value. So, if I plot something else, say Q4, it is stabilized there. Fine. But this is a overdamped system. No, it is a overdamped system. It's overdamped system. So, if it is slightly underdamped, then what is the behavior? Slightly underdamped, I will make it say 0.5. No, 0.8 maybe. 1 was the critical case, right? See, it has gone slightly above and then come back. If you plot it P2 versus Q4, sorry. See, it has gone, but then the large loop and then it is going there, underdamped. So, it is spiral still, but the spiraling is quite different than what you saw initially. Fine. Now, these are the things that you have to understand. I did this deliberately, because when you look at a spiral, or if you derive that it will be a spiral, the spiral may not be all that nice spiral that comes into view like a spiral galaxy or something like that. It is often you have to apply your mind to see that it is a spiral. It is actually spiraling. In this case, it is spiraling into that place, but it is not all that clear. You have to see. You have to apply your mind to see. Good. So, you have understood what happens for 2-dimensional systems. What happens for 3-dimensional systems? See, so far we are doing 2-dimensional systems, 2-dimensional systems that can be plotted on the piece of paper, and we have found that there are exactly 4 different types of behaviors possible. No, there are actually many, but 3 distinctly different cases out of which there can be less than 0 eigenvalue or greater than 0 eigenvalue, depending on that it will be either decaying or growing up, but nevertheless you have understood 3 cases. If you have a 3-dimensional system, which means you will get a matrix which is three by 3 matrix. A 3 by 3 matrix means x dot, y dot, z dot will be in the local neighborhood. This will be the equation, which means it will have to be plotted in x, y and z. Now, what will be the meaning? Still you will be able to apply the same logic. What was the logic? That in order to solve it, we will write down the independent equations and we will compose the general equation out of that. How many independent equations will you need? 3. Now 3. So, you need 3 equations and you will compose the general solution out of that. So, composing 3 equations and obtaining a general solution out of that will require you to compute 3 eigenvalues and 3 eigenvectors. Now, this will lead to a cubic equation for obtaining the eigenvalues. A cubic equation can have what kind of different possibilities? Imagine, earlier we could only say it could be real or complex conjugate. Since if there is a one complex eigenvalue, the other has to be complex conjugate, so 2 always will be complex conjugate. So, if there is complex, it will be complex conjugate and else it will be real. So, either all 3 real or 1 real, 2 complex conjugate, that is the only possibility, nothing more. So, the possibilities are actually limited, not very difficult to figure out. So, if you have this, you obtain the eigenvectors. Again, say it will be an eigenvector like this, eigenvector like that, and say another eigenvector like this. You can obtain 3 eigenvectors. Oh, the arrows may not be like that, arrows will be determined by their eigenvalues. If the eigenvalues are less than 0, it will be inward arrow outside. So, depending on any starting initial condition, the same logic will apply, that you will first look at their projections on the 3 like this, and for this one you have to come down and then you have to go this way. In any case, you have to look at the projection on the 3 eigenvectors, and these projections will either grow or decay depending on the corresponding eigenvalues. So, the dynamics will have to be visualized in the 3-dimensional space, will have to be visualized in the 3-dimensional space, say something like this will happen, whatever it is, but that will happen at every moment. The behavior will be guided by the directions of the eigenvectors, if they are real, the directions of the eigenvectors, and how they either contract or expand along each eigenvector. So, obtaining the exact solution is not all that important. Understanding the behavior is more important. Understanding will come in terms of the values of the eigenvalues and the directions of the eigenvectors. Is that clear? Try to do one problem before we come to the next class. If it is capital X dot is equal to 0 1 0 0 0 1 minus 2 1 2 times x, then what will be the behavior like? How will you do? From this you will obtain the eigen values, from there you will obtain the eigenvectors, eigenvector directions, and then you will say that now I will fix certain coordinate and then obtain the other. As a result, we have got a specific eigenvector, and then we will be able to write down the equation simply as x dot is equal to C1 e to the power lambda 1 t times V 1 plus C 2 e to the power lambda 2 t times V 2 plus C 3 e to the power lambda 3 t times, that is it. Pretty trivial actually, no complication. So, just do this before coming to the next class, fine. Okay, that is all for today.